Hello everyone, my name is Weijun. Today I'll be presenting my internship project that I've been working on through the course of my internship in ChemoPower technology. I'll be presenting on Dang Gui. So for this presentation, I'll be going through the background, methodology, results, recommendations and conclusions for the project. We shall now look into the background of the project. We'll first look into traditional Chinese medicine, commonly known as TCM. It has thousands of years of history, dated back to ancient China, and has been constantly evolving ever since. With its popularity growing worldwide, more and more people are practicing TCM, and yet there's very few scientific basis to back it up, which is why we are looking into it. So why we are looking into TCM? One of our company's vision is to build a TCM database, and my internship project will be helping the company work towards that vision. The herb that I'll be working on is Dang Gui, scientifically named as Angelica sinensis. As you can see from the picture, there's a Dang Gui root, and it's one of the common herbs used in TCM, commonly grown in high altitude mountains in Korea, China, and Japan. The herb is also known as the female ginseng due to the benefits that the herb provides being similar to ginseng, such as increasing energy levels and more health benefits to the female consumers with effects such as menstrual regulations and hormonal balance. There's a problem with traditional Chinese medicine, including Dang Gui. The way that the pricing of the herbs are determined are through qualitative factors such as smell, appearance, and country of origin. There's no scientific basis for the pricing of the herbs. There's no way to quantify it, and this leads to a question: are the pricing of my herbs justified? How do I know I'm paying the right amount for my herb? So this leads to our project objective, which is to obtain the chemical profile of the Dang Gui, and then we want to find the trend between the price point and the chemical profile. And the way that we're going to go about this is through the use of gas chromatography mass spectrometry. I'm sure every one of you remembers using chromatography before. Separation of a mixture through the use of a solvent. GCMS works in a very similar way. We extract the volatile component from the sample and we separate it in the GC column by temperature. The separated gas, upon leaving the column, each will be fragmented into mass spectrum and we'll be collecting its information at its detector. The mass spectrum from the whole run will be consolidated into a TIC, total ion chromatogram. Each of the peak on the TIC is a gas composition extracted from the volatile mixture. The conventional analysis will take the major peaks on the TIC to be analyzed, and each of these peaks will have their mass spectrum taken and matched with a data library to verify its chemical identity. But there's a problem with conventional analysis. It does not take into account of the trace components. As you can see from the TIC, there are many peaks found, but not many are visible by the naked eye. Many of the times, these peaks are neglected, and which leads to a less complete chemical analysis. The other problem with conventional analysis is co-illusion, which is when multiple components reach the detector around the same time. The detector can't differentiate the different components, resulting in the different components appearing as one peak on the TIC. And both co-illusion and trace components is one of the problems with conventional analysis, which leads to a less accurate analysis and a less complete chemical profile. So to address this problem, we'll be using ChemoPower's proprietary data analysis software, Smart Dalton. Smart Dalton, as the name suggests, is a very smart software. It's able to tackle the problem with conventional analysis, which is just stated. As such, we will be able to obtain a cleaner mass spectrum and thus build a more accurate and detailed chemical profile. Now that we have covered on the background of the project, we'll be discussing on the methodology. More specifically, how are we going to approach the chemical profiling of Dang Gui? For the experiment, we'll be taking 4 samples of Dang Gui at different price points to be analyzed and compared. Each sample was run 3 times to ensure consistency of the analysis. The experiment was conducted on Shimazu GCMS QP2020 using Agilent HP5MS semi-standard non-polar column for the GC phase. And the reason why we are using a semi-standard non-polar column is because we are performing an exploratory analysis, which we want to gather as much information as possible from the experiment. And this column takes into account all types of chemicals regardless they are polar or non-polar, which makes this suitable for our experiment. And the experiment of the runs were optimized beforehand. The matching will be done based off the visual symmetry of the analyte mass spectrum with the library mass spectrum, the reduction index value, which is an indicator of how long before the component reaches the detector, and its molecular weight. This allows us to identify and compile the analyte information into a chemical profile where we can use the data for further analysis. For the data analysis, we'll be first using Smart Dalton software to pick up the trace components and separate all the convoluted components. From there, we obtain the clean individual mass spectrum of each components, and this will bring us to our next step, library matching using MoleculeDB. So on the MoleculeDB, the software will take the exported mass spectrums from the Smart Dalton software and help us match the mass spectrums of the analysis to reference mass spectrums from the data library from NIST, National Institute of Standards and Technology. The matching will be done based off the visual symmetry of the analyte of the mass spectrum with the chemical profile that we collected from the analysis. We will now look into the results of the experimental run to attempt to find a trend between the price point and the chemical profile through the use of statistical analysis. We will look into the number of verified components. Every data will be recorded as an average of 3 runs. We were able to identify 276 unique chemicals in the 4 samples of Dang Gui, with Dang Gui 3 having the most number of chemicals detected, followed by Dang Gui 1, Dang Gui 2, and Dang Gui 4. We took the verified components and sort them into their categories based off their chemical nature to perform a comparison. And we were able to find that terpenes have the most number of unique components across the 4 samples, followed by hydrocarbon, carbonyl, alcohol, phthalates, and others. However, we could not get much information from here. So we also looked into the TIC of the 4 samples. On the visual inspection of the TIC, it was found that terpenes and phthalates chemicals are found at the highest abundance in terms of volume across the 4 samples, which these 2 group of chemicals will be our main focus for this project. So what are terpenes? Terpenes are formed when multiple isoprene molecules bond together, and terpenes are found in 60% of all natural products such as cosmetics and essential oil. It is also known to provide benefits to the users. Limonene is an example of a terpene. It is found in citrus fruits and is commonly used as a flavoring agent and is known to have anti-carcinogenic properties. Now that we know about terpenes, we also want to know about phthalates, or more specifically, butyl phthalates. These 6 butyl phthalates are commonly found throughout our samples. They are found in the second highest abundance in volume and is an indicator for Dang Gui. So when they find these chemicals in the plants and the plant products, they are usually narrowed down to a possibility that it could come from Dang Gui. And these chemicals are tested on clinical trials for many potential medicinal benefits, with each having their own distinct properties. Now that we know about the 2 groups of chemicals, we also want to compare the categories of terpenes to find a trend. And we notice that as the price increases, ironically the number of monoterpenes decreases. But that's the only trend we can observe. So because of that, we decided to use principal component analysis to distinguish between the Dang Gui samples using their terpenes profile. Principal component analysis in layman is a tool that we use to create a trend in large data sets. We will look into the explain variance first. We use explain variance to find out how many PCs, principal components, do we use to account for the variances across the samples of Dang Gui. As we can see, with PC1 and PC2, we were able to account for a total of 96% of all variances across all samples. So we will be using just 2 PCs for our PCAs. This is a score plot. We use this to see the relationships between the different samples. The closer they are, the more related they are. As you can see, the average runs are fairly consistent as they cluster together, and the different samples at different price points are distinctly different as they are far away from each other. So this is the loading plot. This is a loading plot. It has all the terpenes profiles inside. The further away each chemicals are from the other, the more likely that one will be present while the other is absent. We isolate the outliers beyond PC plus minus 20 to isolate the chemical components that are more distinguished. When we combine these two plots together into a biplot, we were able to establish visual relationship between the chemical components and the samples. The closer the chemical components are to the sample, the more representative that the chemical components are to the sample at the particular price point. So we took the information and we compiled them together into a table. By combining the two plots together into a biplot, we were able to establish a visual relationship between the chemical components and the samples. The closer the chemical components are to the Dang Gui samples, the more representative the chemical components is to the sample at that particular price point. We compile the information of the representative chemicals into a table, and we can see that alpha-pinene is unique to Dang Gui 1 at a price point of $15.40. Beta-pinene is unique to Dang Gui 2 at a price point of $16.50. Isoepidosine, isomentone, camphene is unique to Dang Gui 3 at the price points of $26. Cuparin, 4,11-amorphadiene is unique to Dang Gui 4 at $49. So using principal components analysis, we were able to distinguish the representative chemicals to each Dang Gui samples at different price point. So we took the 6 common components of the daylights and we plot them into a line graph. We had to scale them down into relative proportions as each component has drastically different volume compared to the other components. And upon plotting a linear regression plot, we noticed that as the price point increases, the amount of daylights also increases. With that, we can conclude that there's a moderate correlation between the amount of daylights inside the Dang Gui and its price point. As the price point increases, there is more daylights present inside the Dang Gui sample. And with that sums up the results of the run. I would like to conclude the project and add my recommendations to it. So for the conclusions, we found that there's a weak correlation to the number of terpenes with the price point. So we're only able to find that there's a decreasing trend of monoterpenes as the price point increases. And we are able to identify unique terpene markers of Dang Gui at different price points. So we found that which chemicals are more representative to a certain price point of Dang Gui. And we're also able to identify there's a weak correlation of daylights to the price point. So as the price point increases, the number of daylights also increases moderately. I felt that more can be done for the project, so I'll be going through the recommendations that I have for it. Firstly, we need a more complete data library. There are many analytes that could not be identified as the data library do not have any information about them. So during library matching, we could not match some analytes as a result, and we do not get a very complete chemical profile. Secondly, we need to use more samples of Dang Gui. Statistically speaking, our sample size of 4 Dang Gui is just too small. It's not enough to be representative of the whole Dang Gui population. Thirdly, we need more information of the samples. Currently, the information that we have of the samples is the pricing. We do not have other information of the samples such as the species, the country of origin, the type of soil it is grown in, and other informations. This could be problematic. For example, 2 Dang Gui samples from 2 different countries could be sold at different price points due to difference in operation costs in the countries. It would not make sense to count both as different samples as it could lead to experimental errors and they are practically the same thing, right? And lastly, we also want to explore more analytical options such as the use of liquid chromatography mass spectrometry (LC-MS). Chemical profile of Dang Gui is only able to account for the volatile chemicals in the Dang Gui, but we also want to know what's the remaining components that's not found in GC-MS. So through that, we explore other analytical options to build a more complete chemical profile of Dang Gui, and this is able to explore more areas to compare the trend between the price point and the chemical profile. With that, I conclude my internship presentation, and I would like to thank Dr. Chua and Ruth for the guidance for this project, and I also like to thank Dr. Mabel and Dr. Zhang for the help with this presentation. Thank you so much for your attention, and I hope you have a wonderful day ahead of you.